All right, what I want to do today is go and finish 8.3, dealing with functions. And then we'll go into algebraic thinking, dealing with equations in the Cartesian coordinate system. All right. This problem, example number 4 that I attempted to do on Monday, where we had a company that can make 10 bridge bulkheads for $54,000, while 18 bridge bulkheads cost $59,200. And we want to find out the cost, or Y of X, of producing X bridge bulkheads. Pretty much I started off by doing this. I subtracted 54,000, which was the cost for making 10 bridge bulkheads, from the $59,200, which was the cost of making 18 bridge bulkheads. That difference was $5,200. And then I subtracted 10 from 18, 10 bridge bulkheads, and then 18 bridge bulkheads. So if I subtract 18 minus 10, that would be 8. And then I divided 8 into 5,200 to get 650. Now that $650 represents the dollar amount per bridge bulkhead. So each bridge bulkhead is $650. Now, I just wanted to find out what would be the cost for just making 10 bridge bulkheads. That's $650 times 10, which would be $6,500. Okay. But they list $54,000 as the total cost. So if I subtract $6,500 for 10 bridge bulkheads from the total cost of $54,000, that amount comes out to be $47,500. And you probably can do the same thing by finding out how much, well, for 18 bridge bulkheads. $650 per bulkhead times 18. Stop sharing so y'all can see this. So 650 times 18, that amount would be like $11,700. And you were told that 18 bulkheads cost that 18 bulkheads, I forgot, will cost, it is $59,200. So subtract 11,700 from the 59,200. That will also be $47,500. Now that $47,500 might be something like overhead, probably labor cost. So the correct function would be this: Y of X is equal to the cost of each bridge bulkhead, that's 6,500 times X, and then plus whatever that $47,000 represents. Okay. So that would be the function for that. Okay. Any questions? Okay. I thought I need to go ahead and cover that. So, okay. All right, the last thing we left off on Monday was functions as arrow diagrams. Okay. Because we kind of spent some time determining whether equations were functions. Okay. All right, in this case here, we can look at diagrams or arrow diagrams to determine whether or not we have a function. All right, in this case here, Arrow diagrams can be used to determine whether a correspondence represents a function. The one on the left does represent a function because notice you only have one value in, let's say, mapping A, going to only one number or one dot in mapping B. So this function right here is a mapping from A to B. Okay, so those arrow diagrams can be called mappings. Now in this one, it's not going to be a function. Because if you look at it, here 0 is paired with 1, 1 is paired with 4, 2 is paired with 4. But here at 3, you've got 3 going to two different values in B, 4 and 10. So this would not represent a function. It would not represent a function, meaning you only got one X value. You got one X value going to two different Y values. So that would not be a function, and we cannot have that. Okay. All right, now let's look at this example here. Example 8. Looking at each one of those, we want to determine which, if any, of the figures exhibit a function from A to B. Okay. And if a correspondence is a function from A to B, we want to find the range of that function. So now let's look at this mapping right here from A to B. Would that be a function? Oh, no, it would not. And what would be the reason for that? Okay. Well, let's look at this. Here, the 1 is going to two different values in B. 1 is going to 2 and 1 is going to 4. Okay. That's why it would not be a function. Okay, take a look at this one. Would that be a function? It would not. B is not going to anything in this B right here. Probably they should label this as X and Y, but here B is not going anywhere to any of these values in mapping B. Okay, questions on that one? Now, how about this third one right here? Would that be a function? This one is a yes, because only X is going to A, the Y is only going to C, and Z is going to B. Okay. And since it is a function, here's what a range of the function. Actually, the range is always the set of all Y values, or the set of Y values for that function. And that's going to be only A, B, and C. We don't include the D because nothing from A is paired with D. So only A, B, and C would be the range of the function. All right, questions on that one? Okay. Now for this one in the lower left, would this be a function? This one would be, because only John is going to Brown, Mike is going to Smith, Joan is going to Brown, and Sue is going to Doe. So that does represent a function. And what about this one? In this case, it would be. Because only the 0 is paired with the 1 is paired with 4, 2 is paired with 7, and 3 is paired with 10. Okay. Any questions about determining whether a function, using an arrow diagram to determine whether or not you have a function? Okay, on the next page, let's say we had tables and ordered pairs, because functions can be represented as tables and also as ordered pairs. Let's say we have the L&B Loan Service distributes the following fee schedule to their customers. It gives the price for mowing large lots given the number of acres in that lot. Okay. So here is what this looks like. And of course, it is a function because you're only going to have like one value for the number of acres to one price. And it also can be written as a set of ordered pairs. So for 1 acre, it's $50, 2 acres, $85, 3 acres, $120, and so on. And the way we can determine whether a set of ordered pairs is a function is we have to look at the x coordinate only. If that x coordinate repeats, then that means that the relation would not be a function. Okay. And by the way, the word relation is just a set of ordered pairs. Okay. So in example 9, parts A and B, we want to determine which of the following are functions from the set 1, 2, 3 to the set A, B, C, D. If the set of ordered pairs is not a function, explain why not. Okay. So in this case right here, I got 1 comma A, 2 comma B, 3 comma C, and 2 comma D. Would that represent a function? Well, let's take a look at that. Because with these, to determine whether a set of ordered pairs is a function, you want to look at all of the, look at your x coordinates. So here, one comma A, and then we got 2 comma B, 3 comma C, and then you got 2 comma D. And in this case, if your x coordinates repeat, as I mentioned, that means you're not going to have a function. There's 2 is paired with B, but also 2 is paired with D. So that tells me that this relation is not a function. Now you could also write this as a mapping from one, let's say the x, to the other, which is going to be y. Your x is going to be the domain. That's all of your x values here, your x coordinates in this case. Here I got a 1 and a 2 and a 3. And then your y coordinates are going to be A, B, C, and D. And then start mapping those two. 1 is paired with A, so here we can map 1 to A. 2 is paired with B, so 2 goes to B. 3 is paired with C, so 3 goes to C. 2 goes. As you can see here, that 2 is going to 2 different letters, B and D. So that's why this is not a function. All right, questions on part A. All right, part B looks like this. 1A, 2B, 2 comma B, and then 3 comma C. Now, would that be a function?
Yes.
This time it would be, because you only got 1 going to A, 2 is only going to B, and 3 is only going to C. So this is a function. Okay. Questions on example 9. Okay. Let's look at this example. Determine if the following is a function or not. Here you got the set of ordered pairs 4, 9, 8, 13, 8, 14, and 10, 15 in the set of whole numbers. Would this represent a function? This time it's no. Because notice that 8 is paired with 13 and also 8 is paired with 14. So you've got an x coordinate with 2 different y coordinates. Okay, so this would not be a function. All right, and what about this one? The set of ordered pairs 15, 20, 19, 24, 20, 25, 21, 30. This time it is a function. Only one x coordinate to only one y coordinate. So in example 11, this would be a function. Okay. Any questions about using tables and ordered pairs to determine whether or not you have a function? Okay, functions can also be represented as graphs. So here, graphs are probably the most commonly known ways of representing functions. So if we wanted to, let's say, plot an ordered pair, A comma B, excuse me. Here we're going to move to the point A, which is actually the x coordinate, but some textbooks usually use this word, the abscissa, which is the same as the x coordinate on the horizontal scale, left or right. And then from there, we move up or down to the point B, which is called the ordinate, or your y coordinate, along the vertical line that goes through A. And in the next section, section 8.4, we'll talk about the coordinate plane. And in example 12, it's just a graph where they did plot some points on the coordinate plane and then connected the dots. Okay. Now this only represents just one quadrant. A positive going across and positive going upward. So here this shows the relationship between the number of cars on a certain road and the time of day for times between 5 a.m. and 9 o'clock a.m. Complete parts A through E below. So in part A, and here some of these do have a choice of answers here. Let's start with part A. What is the increase in the number of cars on the road between 6:30 a.m. and 7 o'clock a.m.? So we look at 6 a.m. and 7 a.m. Now at 6 a.m., how many cars are there? Oh, 400. 6 a.m. Oh, I'm sorry, 6:30 a.m. Whoa, 600. And then 7 a.m., we have to kind of estimate, because that looks like it's halfway between 600 and 700. And in this case, I'm gonna say 650. Okay, yeah, I'm gonna say 650. So if I do 650 minus 600, that would be how much? It'd be 50. So the increase in the number of cars on the road between 6:30, which is between 6 and 7, that's this right here, and 7 o'clock a.m., that would have to be approximately 50. All right, part B is this: during which half hour was the increase in the number of cars the greatest? Okay, 6 to what, 6:30? Okay. And the reason for that is this: here's 6 a.m. and here's 6:30. Notice this line is a lot steeper, or has a slope that's, well, we'll talk about slope later, but notice that it's going up quicker between 400 to 600 cars. That's the biggest jump there. So between 6 and 6:30, that's where the number of cars increased the greatest. All right, now part C is: what is the increase in the number of cars between 8 o'clock and 8:30 a.m.? How much? Well, between 8 and 8:30? Well, actually, you can see that it is a flat line. It's just a straight line. It hasn't changed. Because at 8 o'clock is 700, 8:30 is still 700. So subtract, you'll get 0. So there was no increase in the number of cars between 8 o'clock and 8:30 in the morning. Okay. I'm gonna go down here to part D. During which half hours did the number of cars decrease? During which half hours did the number of cars decrease? Okay, so I'm gonna scroll back up here. Between 8:30 and 9. Because that's the only place where it starts, where the number of cars decreases. That's where this graph is falling. Between 8:30 and 9 o'clock is the only time that the number of cars decreased. And by how much does the number of cars decrease? By 100. Because at 8:30, it was 700. By 9 a.m., it was 600. So 700 minus 600 is 100. And then in part E, the graph of this problem is composed of segments rather than just points. So here, why do you think segments are used here instead of just points? Yeah, it would be D. And that's because here segments are used because the data for times at which the number of cars were recorded are continuous rather than discrete. Now, when you get into statistics, they use those words, continuous and discrete. Because discrete is something that is countable. Continuous means that it goes on and on and on without end. All right, questions on example 12. Okay, here's example 13. So here we want to determine which of the graphs below are graphs of functions and which are which are not. And if a graph is not a function, explain why, or, well, explain why not. So here's graph A right here. Would this graph represent a function? Yes, it would. Okay. Because you only got one X to only one Y. And B, would that be a function? No, it would not. Because this X value has other Y values like 6, 0, then you got 6, 1, 6, 2, 6, 3, 6, 4. Yeah, the same X value to 5 other Y values. That would not be a function. And what about this one, part C? Would it? Yes. It would be. Because this point is 5, 0, 6, 0, 7, 0, 8, 0, 9, 0. Those X values are different. Yes. Because for a function, you only look at the X values. And I don't know if you remember this back in college algebra, but there is something called, if you're dealing with graphs and you want to determine whether or not you have a function, we can use what they call a vertical line test. What you do there is just draw a vertical line through that graph, and if that vertical line crosses the graph in more than one place, then your graph would not be a function. So going back to that graph in example 13, graph B would fail that vertical line test, okay? Because they'll cross the graph in more than one place, whereas A and B would pass the vertical line test, because you're only going to have that vertical line crossing the graph at only one place. So that would be a function. And so would, same thing holds true for C. It would only cross the graph at only one place. Okay, questions on that? Okay. The last thing we'll talk about is the composition of functions. So here in the composition of two functions, the range of the first function must be the subset of the domain of the second function. And here we're using a function machine to illustrate what a composite function looks like. So here you got two functions, f of x and g of x. And in this function machine that you see here, f of x is equal to x plus 4. And then the second one is g of x is equal to 2 times x. So if we put 2 into the top machine, which is your f of x, then that means f of 2 would just be 2 plus 4, which is 6. So the output there would be 6. So now that output for f of x becomes your input for g of x, okay? And g of x is equal to 2 times x. So if the input for g of x becomes 6, then 2 times 6 will be 12. So now f of g of x using that function machine would be 12, okay? And there is a note that the range of the function f is going to be the domain of g. Okay. Because here the range just a set of y values, that'll be a range, and now it's going to become the domain for g. Now, let's look at example 14 where we got a function machine. We're going to put some value of x in that function machine for f of x, which is equal to 5x. Then whatever that is, we'll substitute it for x in the g of x function to get the output of the composition of G with f of x. Okay. All right, so let's take a look at each one of these. Let's say I want to consider those two function machines that are placed as shown and then find the final output of the following inputs. All right, so starting with, so here we're going to start off with part A, which is 6. And I'm going to say here x is equal to 6. So that x equals 6 will go into the first function where f of x is equal to 5x. So here we just substitute the x with 6. So f of 5 times 6 will be 30. And then we got our g of x. In this case, that's going to be x minus 4. And here this time, what we got for f of x, which was 30, that will become the x for g of x. So that means g of 30. And g of x is that x minus 4. So what's 30 minus 4? 6. So that will be the output for f of, well, g of f of x. Questions on part A? Now in part B, we got x is equal to 10. X is equal to 10. Okay, so we start off with f of x. So that means we're going to evaluate f of 10. So 5 times 10 will be how much? So now that 50 becomes our x value in g of x. So g of 50 would be 50 minus 4, which is how much? 46. Okay. So the final output there will be 46. All right, now in part C. Here we got x is equal to the square root of 10. Okay, and we want that final output. So in this case here, f of the square root of 10 and x is equal to the square root of 10. So this will be 5 times the square root of 10. And really, we're not going to be able to multiply 5 times the 10 because the 10 is underneath the radical. So we'll just have to write it as this. Five square root of 10. Okay. And we got 5 square root of 10. That would be the x value for g of x. So here we're going to have g of 5 square root of 10. So here we just replace the x with 5 square root of 10 and then minus 4. And unfortunately, let's say, well, you know, if you were doing this on a probably on some homework platform like my math lab, they will want this as the exact answer. And I'm not going to ask you to give me a decimal value for 5 square root of 10 minus 4. So we can just leave it like this. Okay, questions on part C? Okay, part D was zero. I'll say x is equal to 0. So here I want to find what that is. Let's start with the f of x, or f of 0. 5 times 0, of course, that's going to be 0. And then your 0 will be your x value in g of x. So g of 0 would be 0 minus 4, which is how much? -4. And for E, here we got x is equal to 5/8. And in this case here, we're going to do f of 5/8. So it'll be 5 times 5/8. And that 5 is like 5/1. So 5/1 times 5/8, that would be 25/8. And we're going to use that 25/8 for our x in g of x. So g of 25/8 will be equal to 25/8 minus 4. I'll treat that 4 as 4/1. I'm going to change 4/1 with a denominator of 8. So to do that, I need to multiply the numerator and the denominator by 8. And this will be 32/8, because you have to think of how many 8s are there in 4. There are 32 of them. So 25/8 minus 32/8 will be -7/8. Okay. And part F. Here they just give you the variable n. So here f of n would just simply be 5 times n, or just 5n. Then we use that as our x in g of x. So g of 5n means I substitute the x with 5n and bring over the -4. And that's all there is to it. So f of x is going to be 5n. G of 5n would be n minus 4. Okay. All right, any questions about example 14? Okay, now, this is kind of in more detail for the composition of F with G. And this is how we write the composition of F with G. Sometimes it's read as F circle G. And that's going to be defined by this function. F circle G of X would be equivalent to F of G of X. F of G of X. Where, as you can see here, your inside function is G of X. The outside function is F of X. So if you were to evaluate that, what you'll do there is replace each X in F of X with whatever G of X is. And then we can also have something like this, G circle F, the other way around. G circle F of X. That's going to be G of F of X. Here, the inside function this time will be F of X, G of X is going to be the outside function. What you'll do there is substitute each X in G of X with the F of X function. So in this case here, you have to be given two functions, F of X and G of X, in order for this to happen. Does everyone have this on the board so I can erase this? All right, so here's example 15. So you are given F of X is equal to 4x plus 3, and G of X is equal to x minus 2. So here we're going to evaluate, starting out with the composition of F with G of 6. Okay. The composition of F with G of 6. Now, the composition of F with G of 6 written like this does mean F of G of 6. That's what that means. And here your inside function is G of 6. So we start with what's on the inside, which is this right here. So we need to find out what G of 6 is going to be. And of course, G of X is that X minus 2. So that means we're going to take that 6 and put it in place of X. So it'll be 6 minus 2, which is what? So that means G of 6 is going to be 4. So that means I'm going to be evaluating F of 4. And here F of X is that 4x plus 3. So I'm going to substitute the X and the F of X with the value of G of X, which was 4. So it'll be 4 times 4 plus 3. And when we simplify that, 4 times 4 is 16. 16 plus 3 is 19. So for the composition of F with G at X is equal to 6 will end up being 19. Questions on part A? Part B. Here we got the composition of G with F at 6. Using the same X value, but this time the composition of G with F at 6 is going to be this. G of F of 6. So this time your F of X is the inside function, whereas G of X is going to be the outside function. So I need to evaluate what F of 6 is. So that's going to be 4 times X, which is 6, plus 3. 4 times 6, that's 24. 24 plus 3 is 27. So F of 6 is 27, but I need to find out what G of 27 would be. And this time, what F of 6 was is now my X value for G. So here I'm going to do 27 minus 2, because G of X is X minus 2. What's 27 minus 2? 25. So the composition of G with F of 6 would be 25. Now, if you compare these two, the composition of F with G of 6 and the composition of G with F of 6, you can pretty much see that these two will not be equal. Not going to be equal. Okay. Now, let's take a look at part C. Say we want to find the composition of F with G of X. But that simply means this, F of G of X. Now notice that the inside function is G of X. The inside function here is G of X. Well, what's G of X equal to? X minus 2. So I'm going to replace the G of X with what it's equal to, X minus 2. So I'm going to be evaluating F of X minus 2. However, what's the F of X? 4X plus 3. And I'm evaluating F of X minus 2. So for that X in F of X, I'm going to substitute it with that X minus 2. So it'll be 4 times, and in parentheses, X minus 2, and then plus 3. Okay, because F of X is 4X plus 3. This X is being substituted with what G of X is, X minus 2. So I got 4 times the quantity X minus 2 plus 3. Let's simplify this. 4 times X, that will be 4X minus 4 times 2 is 8 plus 3. What's minus 8 plus 3? Negative 5. Negative 5. So the composition of F with G of X will be 4X minus 5. Okay. Questions on part C? All right, let's say you had the composition of G with F of X. So this time, the G will be on the outside. The inside function is F of X. Since the inside function is F of X, I can go ahead and substitute that with what F of X is equal to. And in this case, F of X is at 4X plus 3. So I'm going to bring down the G and substitute F of X with 4X plus 3. So now I'm going to be evaluating G of 4X plus 3. Well, G of X is equal to X minus 2. So for each X in G of X, I'm going to substitute it with what F of X is. So here, that X will be replaced with that 4X plus 3, and then bring down the minus 2, because that's part of the G of X. And then what's 3 minus 2? Plus 1. So the composition of G with F of X will be equal to 4X plus 1. Okay. All right, any questions about the composition of functions? Or are there any questions about section 8-3? Okay. All right, so that's going to wrap up section 8.3. Okay. Let me